Today we'll talk about the dynamic soaring behavior of albatrosses birds or seabirds, and how this soaring behavior of these birds can be applied in or as an optimization technique. So what is this dynamic soaring? This dynamic soaring behavior of these type of birds is these birds can fly long distance without flapping their wings, and their wingspan is very long, around 3.5 meters, and once they take off, they can fly long distance for a long time, and they can fly as long as 1 year without taking any rest and without flapping their wings. How they do it? I will discuss about this in the first part of the video, and in the second part of the video I will discuss how this behavior of this type of parts can be utilized to identify the optimal points in case of an optimization problem. So what happens is, the albatross bird, they generally fly above the sea surface or ocean surface. Now this ocean surface, due to the wind, they form waves, right? So for this, let us say this is a wave and this is its height, wave height. Sorry, not this. This is the wave height. Okay, this is our wave height. Now, as you know, waves are formed due to three factors. One is wind speed, another one is duration of the wind speed, and another one is swell, wind swell, right? How much amount of free distance the wind is getting to flow. In addition to that, the ocean depth also plays a very important role. So, both the wind speed, both duration it flows, both swell it get, wave will have more heights if it has a specific ocean depth in that area. So what happens is, suppose a bird is flowing like from here to this distance, and you see wind is also flowing at this distance. Due to this wave, this is the peak. As you know, wave have peak and also trough. I think this is well-known fact. These have a peak and these have a trough. So this bird is here. In this trough, in and around this trough, the wind speed here at the trough and wind speed above the peak is different, certainly different. And it is seen that wind speed above the peak is much more compared to wind speed at the ground. Suppose if it is 17 meter per second, this above the peak of wave will have 24 meter per second. So these two different types of wind, or wind having different speeds, is separated by wind shear. Wind shear. So this is just like a gradient, difference between the gradient. So this type of gradient can be seen around 2 meter above sea surface. Now you see the wind flowing here. What it does when it got obstructed with this type of waves, it forms different types of energy. Among these, there is some parts of the wind flows through the wave towards the atmosphere. These are also known as updraft. And also some of the wind creates leeways, eddy currents, etc. That means by striking with this wave, this wind speed is releasing some of its energy. And that is why that energy, those parts of the energy is converted as updraft, leeways, eddy currents, etc. Now what happens when the birds are coming also in the same direction? Wind coming here in this direction, birds also coming in the same direction. What it does is it comes here and it takes the energy from these updrafts, leeways or eddy currents, and it moves upward. It climbs upward. This phenomena is known as climbing, upward climb. But the dynamic soaring gets initiated the moment, due to this obstruction wave, the bird takes a bend. It is known as upward bend. After this bend, there is an upward climb. Now, here in this phase, how the bird is getting the energy to cross this wind shear? It is from the updrafts, it is from the eddy currents, it is from the leeways. And taking this, it crosses the wind shear and gets the higher energy of the wind at this place, above peak. And then what it does, it tries to flow in that same direction again, because the wind is flowing here also in this direction. Now if for any reason the bird wants to come down again here, it takes two moves. One is downward bend and downward dive. And from where it is taking the energy for this downward dive? Because here also again it has to cross this wind shear. Now it is taking this downward dive, taking this energy to cross this wind shear at the time when it is jumping back to its original location. It is not jumping back, we say it will be more correct if I say it is gliding back. Gliding. All the time this bird is gliding only. It never flaps its wings. So what it does is, when it dives, it takes the energy from the downward wind. And at that time, the wind mass flows opposite to the wave. That means the leeway the rear portion of the wind will be towards the face of the wave. If this is the wave, then wind is flowing like this, not like this. And it takes this downward energy from the downward wind and the bird dives into the lower zone or lower phase. If this is zone 1, this is zone 2. You can say this as trough, this as peak, above peak actually. When the bird is flowing like this, wind is flowing like this, though both of them will struck the wave space. This is wave surface. And when wind is striking the wave surface, it is converted into updrafts and eddy currents and leeways, etc. And bird is only, what it does is, it takes the energy from that updrafts and leeways and eddy currents, and it moves upward, it climbs upward. And at the time of diving back to the zone 1, if this I say now, this is zone 1, this is zone 2, the wind must flow opposite to the wave surface, and the bird will take that downward wind, the energy from that downward wind, and jumps into the zone 1, and that energy is actually utilized to cross the wind shear. This is your wind shear. So this is overall the basic behavior of dynamic soaring. This dynamic soaring actually is divided into these 4 parts. One is upward bend, second is upward climb, then downward bend, and third is downward dive. So these 4 consist dynamic soaring. Now I will discuss about how this behavior of dynamic soaring of albatrosses birds can be used to identify the optimal point of any type of optimization problem. Suppose the problem is like this, our very old problem that I have often discussed, y is equal to x square. This is the objective equation, y is your objective variable and x is your design variable. This design variable you have to change to increase y. Your job is to maximize y. Now the constraint is x can be varied in between suppose 1 and 2. It can never take the value of x as 1 or x as 2, but it can take the values of more than 1 and less than 2. So this is a problem. This type of equation is known as objective equation. This is your dv, design variable, and this constraint, this is the constraint. So this is known as constraint. Your design variable must remain within this constraint zone 1 to 2. So if you draw a graph of y and x, this y is x square line will be like this, it will be like this. So if this is 1 point and this is 2 point, so this zone is actually the region of visibility, or acceptability. And this zone is known as region of rejection, region of infeasibility or rejection. So your optimal point must lie in this zone. Because this zone is bounded in both sides by this constant. X can be greater than 1, x can be less than 2. So this is as both the zones, both the sides are bounded, so these are known as closed constraint. If one of the side is open, that means you can take any value. Suppose if I do not use this point is not there. So the constant is only x will be greater than 1. Then this is one-sided constraint. Okay, so as the downward part, the lower constant is there, upper constant is open. So this type of constraint is known as right-handed constraint, and vice versa. If the left is closed, the left-handed constraint. Sorry, this will be your left-handed constraint because left is closed. This one is left, and this one is right. If right is closed, right-handed constraint. So right-bounded constraint, that also is. So whatever may be the case. So what you do is, to increase y, you generate different values of x, which is more than 1 and less than 2. Now, how this different values of x will be generated? This will depend upon the technique you are using. Now, this technique is known as optimization technique. Here you can use any linear programming, non-linear programming, or meta-heuristic algorithm like genetic algorithm, particle swarm optimization, and colony optimization, anything. The way you are generating different values of x is your technique, your optimization technique. So as optimization technique, you can also utilize this Albatrosses dynamic soaring behavior. But how? In this algorithm, what you will do is, you will randomly generate the values of x, and here you will generate 4 different values of x, or 5, n number of x you can generate, n number of values of x you can generate. So this n number of values indicates n number of albatross parts. You can also generate n can be 1 also, 1 to any value of your choice. Now what will happen is, this x value, this random value of x, it is preferable that you use any value in between 0 to 1. That way the dimensionality problem does not arise. So you use any value 0 to 1. So now, but your constant is 1 to 2. So you can use this like this. Lower constant plus higher constant minus lower constant into random function. And this random can be any value in between 0 to 1. But not equals to 0 and equal to 1. Because if you use 0 and 1, then it will create a local minimum. Your optimization process will stuck into, whenever you use x equal to 0, the entire process will become 0. Then and there it is stuck. Sorry, not 0, it is 1. So then and then it will stuck into local minimum. So you cannot use this 0 as well as 1 for the same reason, but any value in between this 0 to 1. And this random value will be multiplied with 2 minus 1, so and added to your lower constant. So this formula is actually like this: lower constant plus upper constant minus lower constant into random. Now here I am using normally distributed random, that is why I am saying 0 to 1. But you can use Poisson's distribution or any other distribution function to generate these random numbers. But this must be within 0 to 1. Now after you have generated the values of x, you put it into this equation y. Then you generated y1. Now similarly you will generate it as you have used n number of values of x. So you will generate n number of values of y in the same manner. Now our goal is to maximize this problem. So what you will do is among these n number values of y, try to identify the maximum y, maximum of all of them. So that will be the most fittest value. So suppose this maximum y is like this, indicated by y max. Then again in the second iteration, again you generate n number of values of x, put it into this equation by putting it into this equation and then into this objective equation. In the second iteration, there will be again n number of y's. And then again you identify the maximum of them. So you have two y's now, one from the previous iteration, another from the present iteration. So 1 and 2. Now if y max of the first iteration is less than y max of the second iteration or the present iteration, then that will indicate that your optimization is in the correct direction. So this type of condition evaluation is also known as your fitness function. You must satisfy this fitness function. Here I am using that whether y is more than the previous one. But you can use other type of fitness function also. If it indicates that it is in the better side, it is towards the optimal direction, towards our desired direction. When it is a y max 1 is less than y max 2, then you again iterate in the third iteration and try to find out what is y max 3. And then you again compare with y max 2. If it is more than y max 2, then you move in the correct direction. You move to the same direction. But the problem arises when it is not greater than y max 2. Or it is equals to y max 2. Or its improvement is at the same rate. Suppose for example if y max 1 is for example 8, y max 2 is 10, y max 3 is 12, y max 4 is 14. It indicates that it is improving, but improving at the same rate. And if it is not generating like this, it is generating like the same value of y max coming up at every iteration for a certain number of iteration after your choice. Then this soaring algorithm will be utilized. How? What will happen is, first you will try to make a upward climb. How you can make this upward climb? With the present value of x, This is your equation to generate the present values of x, correct? You just add another random function which varies in between 0 to 1. So it is actually gaining energy. In a similar manner, the birds get energy for upward climb from the updrafts, correct? So what you are doing is that you are using something more. You are using random, and then again you are generating y. Now if the y is improved compared to the earlier version, earlier iteration, then you move again ahead. But even after adding this random number, if it is not improving, again you use another random number. Now you will say that in this way what will happen is it will move, x will become more than 2. So here what will happen, remember that albatross birds can overcome this wind shear if it is above or around 2 meters above ocean surface. Here also, if the y value is getting more than, the value of x's are getting more than 2, the upper constant, you cannot use this anymore. So at that time what will happen is, but you will try to do a downward dive. Now in case of this downward dive, in this case downward dive, what will happen is you will deduct random function. So you will say that I already used 2 random number added, now I am deducting another random number. So it is does not imply that it will generate the same random number. Random number will arbitrarily pick any value in between 0 to 1. And this minus you can do until the values of x are up to just above 1. Up to that you can minus. Other than that you cannot minus. So this is a very basic algorithm that is using these random numbers are used to overcome the local minima problem. Whenever the algorithm is stuck, that means the same value of y max is given or the same improvement is going on, you imply or you interpret that your algorithm is under local minimum. At that time you have to do what? You have to utilize these random numbers. Similar to the manner the albatrosses utilized extra energy which are extracted from the wave, not only wave slope I will say, or wind updraft it encounters when the albatross is flying in the trough zone. And whenever the albatross is flying in the peak zone, above peak zone, it can release energy and it comes back. Although it takes the energy from their downward wind, so you see why downward wind. So what happens is when it is moving up, albatross and the wind is flying in the same direction. Okay? So when it is moving, flying in the upward zone, above peak, at that time what happens is the yes, both albatross and wind is flowing in the same direction, but opposite to the wave surface. So what is happening? You must know how to indicate this opposite direction behavior compared to the wave surface. At first you are moving towards wave surface, and at the upward side you are moving away from the wave. This thing is indicated by, here it is indicated by the plus random, sorry, and here it is indicated by the minus random. So this way you are avoiding the local minimum, and you are also satisfying the constraint conditions. Similar to the albatross, that albatross cannot cross a wind shear if it is above 2 meter distance from the ocean surface, because it is not sufficient from the energy it can extract from the wind updraft. The energy extracted from the wind updraft, by that energy it cannot process that wind shear or the difference between the two phases of the wind. With that energy, if the wind gradient is differentiated above more than 2 meters of the ocean surface. So that is why these constraints are just like this 2 meter condition. This I have said in the previous slide that if your wind shear is above 2 meters of ocean surface, then only there will be a wind shear and your albatross can cross it with the help of the energy it is extracting from the updraft of wind, which is again created when wind struck with this wave. Sorry. So after getting this energy, it is crossing this barrier, and then it is moving the upward direction, and it is flowing with a more speed. As I say, here at the trough end, if it is flowing like 17 meters per second, the wind is flowing like 24 meters per second above the peak. So when it goes upwards, it takes 24 meters per second, and so it moves more at a more speed compared to when it was here. But when it is seeing that it wants to come back to the trough zone, so what happens is at that time wind must flow outward or opposite to the wave surface. So at that time what happens? Albatross take the energy from this downward wind and crosses the wind shear and come back into the trough. And here also you see it is by this what it is causing dynamic soaring. A cycle is created. This cycle is known as relics cycle, because relics actually observe this behavior of albatross. And here when it is releasing energy minus, it is actually minus indicating the opposite direction of the wind compared to the wave. What is happening is it is actually gaining the energy, but it can gain up to weights. It can gain up to the lower condition, lower constraint. And it cannot go beyond that. So this downward wind has a finite amount of energy that it can share with this albatross. So it cannot extend more energy than that, certainly. And if suddenly this wind stops flowing and albatross has not gained that much of energy to cross the wind shear, then the albatross cannot cross the wind shear and it will flow in the same direction. So this is one of the drawbacks of this algorithm. So anyway, this algorithm is just trying to mimic the concept of dynamic soaring of albatross birds. So you can utilize it. So in summary I can say what happened. Here you are generating n number of x's similar to n number of albatrosses. Randomly you are generating with the help of this formula. Now you are with this formula x you are generating, put it into the optimization equation y is equal to x square, and you see whether y is maximizing or not. So when y is not maximizing at all and giving same value, or y is improving at the same rate, then what happens? You use the upward climb concept. Take some energy as random number, add it to the existing equation of this equation 1, let's say, and then do the same thing, repeat the same thing. And if you see that y is improving very well, that means it has crossed the wind shear. If it has not crossed the wind shear, then again add another random number. Again check it, fitness function is this one. If it is maximized, yes, move ahead to that direction. If it is not, again random number. But up to the higher constant. When it is crossing a higher constant and it is not able to maximize itself, then your next step will be start minusing, deducting random number. This is your deduction. This is your upward climb. You see, this is your downward dive. And these conditions are matched or evaluated at the time of bend. So at the time of upward bend, actually what is doing? It is evaluating the criteria. And in case of downward bend, it is evaluating the criteria, whether it is it is maximizing or not. It may happen that it minimizes. So by deducting, this minus is nothing but it indicates the direction of the wind flow. Plus means it is moving towards the wave surface. Minus means it is moving away from the wave surface. And so minus until x is not equal to 1. When it is becoming 1 or just above 1, you have to stop. So but when you see that by adding random minus random, both way you will test, and ultimately the maximum value of y, the value of x at which the y is maximum, whether it is in case of upward climb or downward dive, anywhere you must take the global maximum and use it as the optimal value of y at x. Last part please understood. You will generate hundreds or thousands of y maxes at the upward direction as well as downward direction. So ultimately what will happen is, it is not that until you will take the y max of the last iteration. No. Because all these things you are just evaluating. You are just randomly evaluating. You will take that maximum of all y's. And corresponding x will be your desired value of the desired variable. So in this way you will end the optimization. Now you will say, what is the advantage? Yes, there is advantage. The advantage is that the easiness of this algorithm. It is very easy to do. Just add random or minus random. Consider the conditions and your work will be done. Simple. As simple as more simple than the relic cycle. Here also we are following a cycle. Improve, improve, improve. This is the boundary. No, I cannot cross this boundary. So let me discuss it in the next. So as discussed in the previous slide, you see this is the cycle. And this is your constraints, C1 and C2. Your albatross starts to fly. These are all upward climb. But here it will stop. This is your upward bound, C1. Then you downward dive, downward dive, downward dive, downward dive, downward dive. Stop, C2. And maybe somewhere here, some imaginary line is there which indicates the wind shear. And this is our wave, correct? And this point is indicating the albatross, the flying of albatross. So this is actually same as the relic cycle or the dynamic soaring. So this cycle may not be as regular as this, because this cycle may be like this, like this, right? But it will be a cycle. Yes, then after completion of the cycle, you check where the optimal point is. It can be here, it can be here, it can be here anyway, anytime. Because at that moment you do not know that this is the ultimate you can get. At this moment. That is why you have to move ahead. So this is the flexibility, this is the advantage of this algorithm. Flexibility. So you can experiment with this algorithm, you can develop this algorithm, a more finer version of this. So initially this is our discovery, that how to use the dynamic soaring behavior of albatross birds in optimization. With this I will close.